This video breaks down how Tesla applies one engineering rule to everything it builds, and why that rule may finally turn car ownership into a near-zero-cost experience. For nearly a decade, Tesla has followed a simple idea. When fewer parts exist, fewer things break, fewer repairs are needed, and ownership stops draining money year after year. With the Model 2 expected to arrive through Tesla's 2026 production line, that idea is no longer theoretical because it becomes a physical machine designed to eliminate failure instead of fixing it. By the end of this video, you'll understand how Tesla's manufacturing system, battery design, structure, and mechanical hardware work together to reduce breakdowns, extend lifespan, and dramatically lower long-term ownership costs, especially for drivers planning to keep one car for decades. Why Tesla removes parts instead of fixing them. In Tesla engineering circles, a phrase has guided decisions for years. The best part is no part, and the best process is no process. Every additional component introduces friction, wear, misalignment, and future maintenance, which is why Tesla redesigns systems by removing steps instead of improving them. For drivers later in life, this philosophy matters more than acceleration or screens, because every eliminated part represents one less failure waiting to happen when repairs become inconvenient or expensive. Traditional vehicles depend on thousands of interacting components that age at different rates, which guarantees rising costs over time. Tesla's approach flips that equation by simplifying the entire system from the factory floor forward.
Zero-defect manufacturing. How failures are stopped before they exist. Tesla's Model 2 production line is designed around dense, continuous quality monitoring rather than post-assembly inspection. Roughly 1,800 sensors track torque, vibration, alignment, frame deviation, and installation force in real time as each module is installed. Every bolt tightened by a robot generates data, including position, applied force, and deviation from tolerance. And when any value drifts outside limits, the system alerts engineers or halts the line immediately. Instead of discovering defects after assembly, Tesla stops them at the moment they form, which dramatically lowers long-term reliability issues. Panel gaps reveal this philosophy clearly. Traditional vehicles accept gaps between 2.0 and 2.5 millimeters, while Tesla's Vision AI system measures and maintains gaps around 0.4 to 0.6 millimeters, reducing misalignment, wind noise, water entry points, and long-term vibration. Tighter tolerances reduce wear before it begins. Behind the scenes, Tesla uses SPC 2.0, a statistical process control system that tracks torque, vibration, equipment temperature, and deviation trends over time. When patterns begin drifting toward failure thresholds, engineers intervene before defects appear, cutting post-production issues by an estimated 50 to 70%. Electrical systems receive similar treatment. Every Model 2 undergoes full electrical diagnostics on high-voltage lines, 12-volt systems, sensors, and control modules, followed by a severe rain test that simulates 2 hours of heavy rainfall under the JIS standard. Even a single droplet inside the cabin sends the vehicle off the main line for correction, which nearly eliminates one of the most frustrating long-term problems: interior water intrusion. Doors and seats, which commonly loosen with age, are aligned by specialized robots measuring hinge parallelism, opening force, and seat rail torque at micrometer precision. That precision determines whether doors still close smoothly after 10 years or require lifting just to latch.
The battery. Why a long-life pack changes ownership forever. Battery lifespan defines the long-term value of any electric vehicle, and Tesla's design target for the Model 2 focuses on extreme durability rather than peak performance. Tesla states that an aluminum-ion battery concept under development targets 1 to 2 million miles of usable life, a figure driven by chemistry, structure, and thermal stability rather than charging limits alone. While lithium packs often show degradation after 1,000 to 2,000 cycles, aluminum-ion cells are designed to tolerate roughly 8,000 to 10,000 cycles, while preserving most of their capacity. That difference determines whether a battery becomes a recurring expense or outlasts the vehicle itself. A tri-layer mesh anode distributes ion pressure during fast charging, allowing the structure to flex instead of cracking, which reduces internal stress and supports repeated high-load charging without accelerated wear. Temperature stability further improves reliability. Aluminum-ion cells operate across a range from -30 to over 50 degrees Celsius, maintaining performance in climates where lithium packs often degrade faster. Material selection also matters. Aluminum remains abundant, recyclable, and less volatile than lithium markets, allowing Tesla to build durable packs without relying heavily on unstable supply chains. Improved safety happens as well. Aluminum-ion chemistry resists thermal runaway, meaning faults generate localized heat without escalating into chain reactions, reducing both fire risk and long-term insurance costs.
The structure: how one cast body can last 30 years. The Model 2 hides its most important durability advantage beneath its minimal exterior. Tesla uses a 50,000-ton gigapress to cast nearly the entire lower body as a single structure, replacing hundreds of welded components found in traditional frames. A typical vehicle contains 300 to 400 welds, each acting as stress concentrators under vibration, torsion, and temperature changes. The Model 2 reduces that count to roughly 12 welds, lowering structural cracking risk by up to 95%. Torsional rigidity illustrates the result. The Model 2 reaches approximately 65,000 to 70,000 Newton meters per degree, around 230% higher than the already stiff Model Y, allowing doors, windows, dashboards, and seat mounts to remain aligned for decades. Tesla coats the cast structure with Gigav Ultra, an advanced anti-corrosion layer designed to resist rust for 25 to 30 years, even in regions where road salt accelerates frame decay. Fewer joints also mean less vibration transfer into the cabin. By reducing joint count, the cast body cuts vibration by roughly 28%, which lowers fatigue across hinges, electronics, mounts, and interior hardware.
The hardware. Which parts quietly remove maintenance? Long-term costs rarely come from major failures, but from small mechanical components that wear gradually. Tesla redesigned these weak points on the Model 2 to extend service intervals dramatically. Traditional rubber suspension bushings degrade under heat and torsion, often requiring replacement within tens of thousands of miles. Tesla replaces them with elasto-composite suspension elements made from elastic polymers and reinforcing fibers, allowing suspension modules to last roughly 500,000 to 800,000 miles without replacement. Wheel bearings receive similar attention. Instead of conventional steel bearings, the Model 2 uses hybrid ceramic bearings with heat-resistant lubrication, extending lifespan to roughly 300,000 to 500,000 miles while reducing noise and rolling resistance. Door hinges, another hidden failure point, use anti-sag alloys tested for approximately 300,000 open-closed cycles, preserving alignment for up to 30 years. These changes quietly remove the parts that drain budgets over time.
What this really means for owners. The Model 2 shows what happens when a vehicle is designed to eliminate failure instead of managing it. Manufacturing precision reduces defects before ownership begins. Battery chemistry extends powertrain life beyond replacement cycles. Structural casting preserves alignment for decades, and hardware redesign removes wear points entirely. For drivers planning one final vehicle, This changes the definition of ownership. A car that ages slowly reduces stress, limits unexpected expenses, and preserves independence longer.
The question that matters most: if a car rarely breaks, rarely needs service, and quietly lasts for decades, ownership stops feeling like a financial obligation and starts feeling like infrastructure. This is Tesla's clearest vision of durability made real. Now, consider this carefully. If you could buy one vehicle designed to last most of your remaining driving years with almost no maintenance, would that change how you think about ownership? Share which design choice matters most to you, and stay tuned for what Tesla builds next.